In this lecture, we are going to study gain margin and phase margin, which are very important parameters for finding the relative stability. The gain margin is a factor by which the gain of a stable system is allowed to increase before the system reaches to the verge of instability. It can also be defined as the reciprocal of the open loop transfer function gain of the frequency at which the phase angle becomes minus 180 degrees. The frequency at which the phase angle is minus 180 degree is also referred as phase crossover frequency. For finding the gain margin of a random system, our first step should be to find the phase crossover frequency, and we can find that by putting the value of phase of open loop transfer function equal to minus 180 degree. After finding the phase crossover frequency, we then have to find the gain at the phase crossover frequency. After that, gain margin is simply the reciprocal of that particular gain, and if required, we can also convert the gain margin in dB scale. Similarly, we have phase margin, which is the amount of additional phase lag at the gain crossover frequency which is required to bring the system at the verge of instability. The frequency at which the magnitude of the open loop transfer function is unity is referred as gain crossover frequency. The phase margin is 180 degree plus the phase angle of the open loop transfer function at the gain crossover frequency. For finding the phase margin of any random system, our first step should be to find the gain crossover frequency. After that, we have to find phase of the open loop transfer function at gain crossover frequency, and finally we will find the phase margin equal to 180 degree plus the phase of the open loop transfer function at gain crossover frequency. Now we will try to follow these steps for finding gain and phase margin of standard second order control system. We are well aware of the transfer function as well as the open loop transfer function of second order control system, and from that we will get gain and phase of open loop transfer function after assuming the system to be unity feedback system. We are assuming unity feedback system for simplicity only. By using only these two formulas, we should be able to find the gain margin and phase margin of the second order control system. At phase crossover frequency, we know the phase angle is equal to minus 180 degree. After solving the equation, you will get the phase crossover frequency tends to infinity, and as such, when you will put the value of phase crossover frequency in the formula of gain margin, you will get the gain margin to be tending towards infinity. Similarly, for the phase margin, our first step should be to find the gain crossover frequency, and for that we have to equate the open loop transfer function gain to be equal to 1. After solving the equation, you will get gain crossover frequency to be equal to natural frequency omega n multiplied by under root of minus 2 zeta square plus under root of 4 zeta raised to the power 4 plus 1. Now you have to simply put the value of gain crossover frequency in the equation of phase margin, which is equal to 180 degree plus the phase shift provided by the open loop transfer function at gain crossover frequency, and by doing that you will get the expression of phase margin to be equal to 90 degree minus tan inverse of under root minus 2 zeta square plus under root 4 zeta raised to the power 4 plus 1 divided by 2 zeta. There is one trigonometric identity which is tan inverse x plus tan inverse 1 upon x equal to 90 degree. By using this identity, we can slightly modify the expression of phase margin such that it is equal to tan inverse of 2 zeta divided by under root of minus 2 zeta square plus under root of 4 zeta raised to the power 4 plus 1. In different books, any of these two formulas could be present. There are a few more interesting facts which you should know after assuming the open loop transfer function is itself stable. Keep in mind, for finding the relative stability of a system, we first have to find its open loop transfer function, and here it is assumed that the open loop transfer function is stable itself. Then only these 3 points will be applicable. For a stable system, the gain of the open loop transfer function at phase crossover frequency is smaller than 1, and the phase shift at gain crossover frequency will be greater than minus 180 degrees, so that the gain margin and phase margin both are positive. Also, the gain crossover frequency is smaller than phase crossover frequency. For marginally stable systems, the gain of the open loop transfer function at phase crossover frequency is equal to 1 and the phase shift at gain crossover frequency will be exactly equal to minus 180 degrees, so that the gain margin and phase margin both are equal to 0. Also, the gain crossover frequency is exactly equal to phase crossover frequency. For unstable systems, however, the gain of open loop transfer function at phase crossover frequency is greater than 1 and the phase shift provided by open loop transfer function at gain crossover frequency is smaller than minus 180 degree, so that the gain margin in decibel and the phase margin both are negative. In this case, the gain crossover frequency is greater than phase crossover frequency. Gain margin and phase margin are very important parameters. You should clearly understand what are these parameters and how to find them.